Hello, Dan Nedelkovsky here from howtomechatronics.com. In this tutorial, we will learn how the MEMS accelerometer, gyroscope and magnetometer work and how to use them with the Arduino board. Also, with the processing development environment, we will make some practical applications using the sensors. First, let's briefly explain how each of these microelectromechanical systems or MEMS sensor work. We will start with the accelerometer. It measures acceleration by measuring change in capacitance. Its microstructure looks something like this. It has a mass attached to a spring, which is confined to move along one direction and fixed outer plates. So when an acceleration in the particular direction will be applied, the mass will move and the capacitance between the plates and the mass will change. This change in capacitance will be measured, processed, and it will correspond to a particular acceleration value. Next is the gyroscope, which measures angular rate using the Coriolis effect. When a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this. A mass that is constantly moving or oscillating, and when an external angular rate will be applied, a flexible part of the mass would move and make the perpendicular displacement. Okay, now let's explain how the magnetometer works. It measures the Earth magnetic field by using Hall effect or magnetoresistive effect. Actually, almost 90% of the sensors on the market use the Hall effect, and here's how it works. If we have a conductive plate like this and we set current to flow through it, the electrons would flow straight from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow and the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means that if we put a meter now between these two sides, we will get some voltage which depends from the magnetic field strength and its direction. The other 10% of the sensors on the market use the magnetoresistive effect. These sensors use materials that are sensitive to magnetic field, usually composed of iron and nickel. So when these materials are exposed to magnetic field, they change their resistance. Okay, now let's connect these sensors to the Arduino board and make some use of them. As an example, I will use the GY80 breakout board, which has the following sensors: ADXL345 3-axis accelerometer, L3G4 200D 3-axis gyroscope, MC588 3L 3-axis magnetometer, and also a barometer and a thermometer, which we won't use in this tutorial. First, let's hook up the board to the Arduino. This board uses the I2C communication protocol, which means that we can use all the sensors with just two wires. So in order to make the communication between the Arduino and the sensors, we need to know their unique device addresses and their internal register addresses for getting the data out of them. These addresses can be found from the datasheet of the sensor, and I have attached links to each of them on my website. For more details how this communication works, you can check my I2C communication tutorial. Okay, now let's see the codes for getting the data from the sensors. We will start with the accelerometer. First, we need to include the Arduino wire library and define the registers addresses of the sensor. In the setup section, we need to initiate the wire library and start the serial communication, as we will use the serial monitor for showing the results. Also, here we need to activate the sensor or enable the measurement by sending appropriate byte to the power control register. And here's how we do that. Using the wire.begin transmission function, we select to which sensor we will talk, the 3-axis accelerometer in this case. Then, using the wire.write function, we tell to which internal register we will talk. After this, we will send the appropriate byte for enabling the measurement. Using the wire.end transmission function, we will end the transmission, and that will transmit the data to the registers. Now in the loop section, we need to read the data for each axis. We will start with the x-axis. So first we will select to which registers we will talk, the two x-axis internal registers in this case. Then using the wire.requestFrom function, we will request the transmitted data or the 2 bytes from the two registers. The wire.available function will return the number of bytes available for retrieval, and if that number matches with our requested bytes, in our case 2 bytes, using the wire.read function, we will read the bytes from the 2 registers of the x-axis. The output data from the 2 registers is 2's complement, with x0 as the least significant byte and x1 as the most significant byte. Using these expressions here, we can convert these bytes into float values from -1 to +1 depending on the direction of the x-axis relative to the Earth acceleration or the gravity. We will repeat this procedure for the 2 other axes, and at the end we will print these values on the serial monitor. Here's how they appear. Okay, now for getting the data from the gyroscope, we will have a similar code as the previous one. So first we have to define the register addresses and some variables for the data. In the setup section, we have to wake up and put the sensor in normal mode using the control register 1 and also select the sensitivity of the sensor. For this example, I will select the 2000 dps or degrees per second sensitivity mode. In the loop section, similar to the accelerometer, we will read the data for the x, y and z axis. Now the raw data has to be converted into angle values. From the datasheet of the sensor, we can see that for the 2000 dps or degrees per second sensitivity mode corresponds a 70 millidegrees per second per digit unit. This means that we have to multiply the raw output data by 0.07 in order to get the angular rate in degrees per second. Now, if we multiply the angular rate by time, it will give us the angle value. So we need to calculate the time interval of each loop section, and we can do that by using the millis function at the top and the bottom of the loop section, and we will store its value into this dt variable. So for each executed loop, we will calculate the angle and add it to the final angle value. We will do the same for the 2 other axes, and at the end we will print the results on the serial monitor. Here's how they appear. The pen shows the x-axis of the sensor, so if I rotate the sensor around that axis, we can see the change of the angle on the serial monitor. Keep in mind that the gyro results are not stable because they drift as the time goes, so in order to get accurate angles, we have to combine it with the accelerometer. Here's an example of that, combining the gyro and the accelerometer data, as well as a complementary filter for smoothing the results. So the data from the sensors and the Arduino board are sent to the processing development environment, and they are used for controlling the orientation of the 3D object. You can find more details and the source codes for this example on my website. What's left now is to see how to get the data from the magnetometer. Again, we will use a similar technique to the previous one. First, we need to define the register's addresses, and in the setup section, set the sensor in continuous measurement mode. In the loop section, we will get the raw data for each axis with the same method as for the previous sensors. Now we need to convert the raw data into magnetic field value or Gauss units. From the datasheet of the sensor, we can see that the default sensitivity mode is 0.92 milligauss per digit. This means that we need to multiply the raw data by 0.00092 in order to get the Earth magnetic field in Gauss units. At the end, we will print the values on the serial monitor. Here I have marked the North Pole on the paper, and the pen shows the y-axis of the sensor. Now if I point the y-axis to the North Pole and tilt the sensor around 45 degrees, I will get the maximum value of around 0.6 Gauss. The tilt angle depends on your location. For example, if you are at the equator, you don't have to tilt the sensor because the inclination at that location is 0. Or if you are at the North Pole, you will have to tilt the sensor 90 degrees. Here is a cool looking application of the sensor, a digital compass made using the processing development environment. You can find more details and the source code of this example on my website. Thanks for watching, and for more tutorials visit my official website howtomechatronics.com.